Problem number 4. In 0G airplane rides, passengers can float around the cabin as if they were weightless. A flight trajectory for such a ride is shown below, with a few points during the journey labeled. Which of the following statements is correct? Take A to be the acceleration of the plane during the 0G part of the flight. Solution for problem number 4. The 0G segment corresponds to the part where the airplane falls freely with the passengers inside. That is, during the 0G segment, the acceleration is g downward, and hence a concave down parabola, corresponding to the segment from B to D. That was answer C, which is the 0G flight begins at B and ends at D, during which A equal G and A points down. That was solution for problem number 4. Problem number 5. A mote of dust is initially located at distance r from the Sun, which has mass big M. At this point, the mote has a small tangential velocity v. Which of the following is a good approximation for the distance of closest subsequent approach between the mote and the Sun? Solution for problem number 5. Here we can use two expressions for total energy. From one hand, total energy equal potential energy plus kinetic energy, which is equal to 1/2 mv square minus g small m big M over r. This is for furthest point. But from other hand, we have expression for total energy for elliptical orbit. That's equal to negative g multiplied by m small m big over a, where a is a big axis of the ellipse, which is smallest distance r prime plus furthest distance r. Now we can equalize these two expressions for total energy to each other, which is give us this formula, and we have this expression. Here this member and this member cancelled, and also because big R much greater than r prime, we have this inequality, so we can neglect this second member and rewrite full answer in form of r square plus v square over 2gm, which is answer C, and that was solution for problem number 5. Problem number 6. A three-legged table is shaped like a uniform equilateral triangle and has identical legs at each corner. When the mass of an object placed on the center of the table exceed m maximum, the table's legs will all simultaneously break. Which of the following shaded regions shows the area within which an object of 2m max over 3 can be placed without breaking any legs of the table? Solution for problem number 6. Due to symmetry, we have maximum mass which could be held by one leg is m maximum over 3. It means that if we put this mass 2m maximum over 3 in some point of triangle table, each force on each leg could not exceed m max over 3. Let's place our triangle and count all corners by letters A, B and C. Let's place our mass on distance y from base side BC, and the total height of the triangle is h. So it means that we can write two equations for equilibrium. First equilibrium equation is Fa plus Fb plus Fc equal 2m max over 3. Second equation is equilibrium rotation about any axis. Let's take axis through our point mass parallel to base BC. Around this axis we can write equation for equilibrium. Fa multiplied by h minus y equal Fb plus Fc multiplied by y. Here, because axis going through our point mass, this point mass does not create any torque around this axis. Now we can write from last equation that Fb plus Fc equal Fa multiplied by h over y minus 1. And let's put this expression to our first equation. So we have Fa equal 2m maximum over 3 divided by h over y. And because Fa must be less than m maximum over 3, we can put this expression to this equation and find that we must have this inequality. And from this inequality we have h over y must be greater than 2 and y must be less than h over 2. So it means that mass must be placed on distance less than h over 2 from each side, BC, AB or AC. And this condition could be good if we choose answer A and place our mass inside of this shaded triangle. So correct answer is A, and that was solution for problem number 6.